Hi everyone. Today I want to present about Otto cycle. So our group member is Cheng Jia Sen and the second one is me and my name is Lee Jia Jun and our lecturer is Dr. Abdul Rashid bin Muhammad Yusuf. The objective is we need to understand the working principle of thermodynamics and we need to discuss the importance of the theory of thermodynamics in each phase of real-life application.
Nicolaus August Otto built the first four-stroke piston cycle of internal combustion engine to improve the efficiency of the Renault engine. It helped to revolutionize transportation. Because of his modern prototype, Wright brothers used gasoline power with this engine to power their aircraft. Because their earlier design is based on German Dr. A. Otto in 1870.
The Otto cycle is an ideal thermodynamic cycle that requires four strokes with a piston intact compression, ignition and exhaust. The fuels and air mixture is compressed and electric spark ignites it. The sudden expansion pushes the piston producing a power stroke and the spring action of the piston pulls the combusted gas away. The Otto cycle is a thermodynamic process that explains the transformation of gasoline's chemical energy into thermal energy within spark ignition internal combustion engines. It involves a series of pressure, temperature, volume, and heat exchange changes, ultimately converting fuels into motion. This cycle is utilized in both two-stroke and four-stroke engine configurations. The advantages is good reliability with performance. The cycle is more suitable for light vehicles that can on a petrol engine. Low cost of manufacturing the engine based on this cycle. High power-to-weight ratio of the engines design with the Otto cycle theory. The limitation is to low and medium-duty petrol vehicles only. The cycle is not valid for diesel engines. It has lower efficiency than the Carnot cycle and hence is not used in power generation plants.
In application, most modern automobiles on the road use the Otto cycle to produce work by converting energy. After the decline of two-stroke engines, the Otto cycle gained popularity in the four-stroke engine category. These engines are now used in cars, scooters, racing vehicles, mopeds, ship trains, and airplanes also.
Now we look at the PV diagram. So um, wait, for the first one, process from 0 to 1, a constant pressure is drained into the piston cylinder arrangement. Process 1 to 2, the piston moves from the bottom dead central TDC to the top dead central TDC, compressing the fuel and air charge in an ideal particle compression. So next, process 2 to 3, the heat is transferred from an external source at a constant volume to the shaft. While the piston is still at the TDC, the mixture rapidly burns in the process. So process 3 to 4, when the mixture burns, it expands adiabatically or isentropically. This is called the power stroke. So for the process 4 to 1, the heat is rejected from the air at constant volume at the end. At the end of the cycle, the piston will be at the EDC in the process. So process 1 to 0, this is the exhaust stroke where the mixture is released into the atmosphere. Now we look at the isentropical compression, which is process 1 to 2. The fuel and air undergo isentropically compression constant, which is constant entropy. This is the compression stroke where the air fuel mixture is adiabatically compressed compressed as the piston moves from PDC to TDC. The related formula is delta H equals to delta Q plus B times delta P, or equals to T delta S, T dot delta S plus B dot delta P. During isentropic conversion in the Otto cycle, delta Q equals to 0. Hence, for an ideal case, we can say that delta H equals to V dot delta P, del W equals to H2 minus H1. And the related formula is V1 equals to V2 over equals to T2 over T1 power 1 over K minus 1. So we look at the isochoric compression, which is process 2 to 3. The heat is transferred to the mixture at a constant volume from an external source, while the piston is at TDC. The process increases the temperature and entropy of the system. Based on the first law of thermodynamics, delta U equals to delta Q minus delta W. Delta U equals to delta Q minus P delta V. Since it is isochoric, P delta V equals to 0, delta U equals to delta Q. Therefore, delta U equals to 0 equals to Q minus W. So, hence, the final will get W equals to Q. And so, we look at the isentropical expansion, process 3 to 4. The mixture undergo combustion followed by isentropic expansion, decreasing the temperature and volume. The gas expands diabatically as the piston moves from the top dead center to the bottom dead center. Due to this expansion, the gas lost internal energy that is equal to the work. The volume change with a ratio called the isentropic expansion ratio, which is equal to the compression ratio of the Otto cycle mathematically. And then last, isochoric exhaust, process 4 to 1. It is rejected at a constant volume from the system as the exhaust valve open at step 4, decreasing the entropy and temperature while the piston is at PDC. The process is also dropped and the process flow from step 4 to step 4. After this process, the gaseous mixture is expelled from the cylinder. Consider the maximum work output, a condition where T2 equal to T4 equal to surd 3 equal to surd T1 dot T3. And then next, we look at the thermal efficiency. Thermal efficiency is the ratio of work done to the input heat QH at the working temperature. And then we can see that the final will get equal to eta equals to 1 minus 1 over R over gamma minus 1. This is where gamma is the compression ratio. R is the compression ratio, and then gamma is the ratio of Cp over Cv. And then this is the graph of the compression ratio with different values. Hence, we look at this is our reference, and then thank you.